So let's now talk about the properties of the Laplace transform. Well, the first one, you're going to get used to that now, I guess, is linearity. Okay, what does that mean? And that's obviously just coming from the linearity of the integral, the Laplace transform of lambda times f1 plus f2, well, applied to some variable s, is just going to be lambda Laplace transform of f1 plus of s plus Laplace transform of f2. Okay, and that just comes from the linearity of the integral. Let's see a bunch of more properties. So we're going to have the Laplace transform, well, modulation, what's called usually modulation, when you multiply your function by some exponential. What do we get? We are going to get that it's, well, let's see what it gives us. The integral from 0 to plus infinity of EAT f of t times e minus s times t dt, which of course you can see as, sorry, that was AAT. That's just going to be the integral between 0 and plus infinity. You can put together the integrals, the exponentials, so that's minus s minus a times t dt, and that is just going to be the Laplace transform of your function f times, well, applied to variable instead of a variable s, that's variable s minus a. Okay, next one. Well, first maybe we should say that it just works for any a that is in C. Okay, next one, let's do, well, the contrary. Let's say that we've got a greater than 0, and we're going to make the Laplace transform of f applied to t minus a. So I'm shifting my function. So we must be careful here when we apply the formula. So we must always think that our function is multiplied by a heaviside function, so that it's only defined when it's greater than 0. So if I had my function f of t, which was actually f of t times h of t, that's actually a good habit that we should take when we apply Laplace transform. We should think as I'm applying Laplace transform to some function times the heaviside function. So when I'm doing f of t times, f of, that's the point. If I want to do that shift, if I want to do f of t minus a times h of t minus a, when is that going to be greater than 0? So we have f of t minus a is equal to 1 and 0. It's equal to 1 when t minus a is greater or equal to 0. Okay, in other terms, when t is greater than 0, well, than a, sorry. Okay, and 0 when t is smaller than a. So that when we write now the formula for this Laplace transform, if a is greater than 0, that's going to be the integral between a and plus infinity of f of t minus a e minus s times t dt. Okay, so as usual, we're going to make a substitution. Let's put capital T is equal to T minus A, D capital T is equal to dt, and that's giving us, thanks to that well managed substitution, that's going to give us, so now when small t is equal to A, big T is going from 0 to plus infinity, f of capital T e minus s small t is now capital T plus a, s times t plus a, d big T, so that this is really, I can factor with e minus s times a, integral between 0 and infinity, f of t e minus st dt. So what do we get? We get exponential minus s times a times the Laplace transform of my initial function. Okay, so as it happened actually for the Fourier transform, we've got something very symmetric here. When you are doing some modulation of your original function, you get a shift of your Laplace transform. And conversely, when you're doing a shift of your original function, you get your Laplace transform multiplied by a minus sa. Okay, so don't worry. We're going to use you're going to have some reminders of the formula most of the times. All right, but it's something that you by habit you will come to learn them anyway. Okay, so let's compute some other Laplace transform using that result. So we had obtained previously, we obtained that the Laplace transform of the Heaviside function was 1 over s. Okay. Now, what are we going to get if I want to find, and so we said that works for real value of s strictly greater than 0. That was the domain of my transform. Okay, now let's compute the Laplace transform of exponential of a times t for some a belongs to c of, well, as we said, we should always think of them as being multiplied by h, the Heaviside function, times of t. So that's using the previous formula. That's just going to be the Laplace transform of h of t applied to s minus a. So that we get that the Laplace transform of some exponential is 1 over s minus a, and the convergence domain is that real value of s is strictly greater than the real value of a. Okay, so in order for, if we look at this formula, why do we need this convergence domain? Because we need that this integral still goes to 0 as t tends to infinity, so we need that the real value of s is greater than the real value of a, strictly greater than the real value of a. Otherwise, it's not going to give you something that tends to 0, on the contrary. Okay, doing some very similar work, you can find the Laplace transforms of where you can try sinus h of a times t, cosine h of a times t for some value a. So if you have time, you can do that now. So just pause the video and do that, and you can find the solutions in any Laplace transform tables. If you don't, well, keep in mind that later on you will have to do these kind of basic calculations. Okay, let's go on with the properties. Next property, let's see what it gives you if you're scaling your function. So Laplace transform of, let's take some beta times t, and we need s. And so if we want this to be in the positive domain, let's take some beta greater than 0. All right, so what is that giving me? This is giving me, so the integral from 0 to plus infinity, f of beta times t e minus s times t dt. Okay, as usual, I'm going to do some substitution. Let's put capital T is equal to beta t, so that d capital T is beta dt, d small t. In other words, I've got dt is equal 1 over beta d capital T. Let's plug now the substitution. When small t is 0, well, big T is going to be 0. If I took beta greater than 0 at plus infinity, it's not going to change. And then I've got f f of capital T. I've got exponential minus s capital T over beta times dt, which gives you then 1 over beta d capital T. So what do we get? That's going to be 1 over beta times the Laplace transform of your function, of your original function, but applied now to the variable s over beta. Okay, so that's another one of the properties that we can use. Next, we will see properties related to derivatives.